Okay, assalamualaikum and a very good morning. So now we go for the second part of the compensator, which is called the phase lag compensator. Okay, for the phase lag compensator, we also have the procedure to design the phase lag compensator. However, the procedure is actually quite long compared to the phase lag. And then we need to use a lot of the information from the board diagram in order to design the phase lag compensator. Okay, for the introduction, the advantages of the phase lag compensator is to improve the steady state response, and also the second one is to reduce the steady state error. Okay. The compensator transfer function is given as follows. So we have G lag of S equals to K multiplied with S plus ZC over S plus PC, where in this case PC is greater than 0 but less than ZC. Okay. And normally the compensator or phase lag compensator can be expressed as follows. G lag of S is equals to K alpha multiply with S plus 1 over T over S plus 1 over alpha T for alpha greater than 1. Okay, so same like the phase lag. Before we design the phase lag compensator, we need to know the design specifications. So this figure shows the board plot of the second order closed loop transfer function, which is in the magnitude only. And from there, actually it is in the frequency domain, and there are 4 types of design specifications in the frequency domain. Okay, the first one is the resonant peak MP. The second one is the resonant frequency omega p. The third one is bandwidth omega b. Okay, and as you notice, all these three consists of the damping ratio information, so that you can calculate MP, omega p, and omega b. The final specification is the phase margin, phi of m, and similarly you can calculate phi of m from the information of the okay. Note that all the stated specifications are in frequency domain, and they consist of the damping ratio term, which you can also obtain from the time domain specification as follow. Okay, if we give you overshoot, you also can calculate damping ratio, and from there you also can calculate settling time and also the peak time. Then the compensator is basically can be designed based on the given frequency domain or the time domain specifications. Okay, so we go for the step-by-step procedure in designing the phase lag compensator. So the first step, calculate the bandwidth omega b that is required in fulfilling the design requirement, such as overshoot, settling time, and peak time. So you can use this formula omega b. Okay, and notice that you can calculate omega b if we give you, for example, the overshoot values. Okay, then from overshoot you can calculate damping ratio. Then from the damping ratio you can calculate omega b. Step number 2, find the value of gain k for the uncompensated system that fulfill the required steady state error gain kp, kv, and ka. Otherwise, let k equals to 1. Okay, so in this case, I show again the example. Okay, given g of s as follows, you need to find k such that kp equals to 3. So you use the knowledge from chapter number 4 on the steady state error, so you can calculate k. Okay, so in this case, k equals to 6. Step number 3, plot the board diagram using the value of k from step number 2. Okay, you can use Scilab or MATLAB to plot the board diagram. Step number 4, calculate the compensated phase margin, phi m comp, that fulfill the design specifications. Okay, so from the design specification, for example, from the overshoot, you can calculate damping ratio. Then from the damping ratio, you can calculate phi m comp. Okay. Step number 5, calculate the additional phase. So in this case, it is called phi m lag. Okay, so you use this formula, phi m lag equals to phi m comp plus 10 degree. So 10 degree is just a bias. Alright, step number 6, find the cross frequency Fg from the board plot that produce phi m lag. Okay, like I said, in designing the phase lag, you use a lot the board diagram information. So step number 6, you need to find cross frequency Fg. So how? From this board diagram, okay, there is a phi m lag. You already know this phi m lag, which is you calculate from the previous step. Okay. Then from this phi m lag, you can project a line to the x-axis, which is the frequency domain, to find Fg. Okay, step number 7. Okay, you already know Fg. Then find the magnitude value Gm in decibel at Fg from the boot plot. Okay, so you just project a line from the Fg to the magnitude, and then when it touches the magnitude line, project it to the y-axis to get the value of Gm. Okay, so this Gm is in decibel. Okay, step number 8. Draw the asymptote line on the magnitude plot at the magnitude of minus Gm. Okay, minus Gm. So you need to draw this asymptote line in this blue dash line at the minus Gm. Okay, so please put the negative sign, okay, or the opposite of produce Gm previously. Okay, step number 9, choose the location of value 1 over t, which is 1 decade lower than Fg. Okay, 1 decade lower than Fg, so it will be to the left side. Okay, so 1 decade lower is basically Fg over 10. Okay, so that one is basically 1 over t. Step number 10, draw a line from Fg over 10 until intersect with asymptote line and name it as a point Q. Okay, so draw this dash yellow line until intersect with the asymptote line, the blue dash line. So the cross section point is we call it point Q. Step number 11. Okay, draw a line with the slope of minus 20 dB per decade from Q until 0 dB line and name it as point P, and the frequency at point P is 1 over alpha t. Okay, so I hope you know on how to draw this slope, okay, minus 20 dB per decade from Q until 0 dB line, until it crosses the 0 dB line. So how? Okay, this one. It is given by this cyan color line. Okay, so when this minus 20 dB per decade line cross the 0 dB, this cross section, we call it a point P. Okay, so this point P, the frequency at this point P is 1 over alpha t. Alright, so then step number 12, calculate K alpha. Okay, where K alpha, you use the information from the minus GM. Okay, 20 log K alpha equals to minus GM, so then you can calculate what is the value of K alpha. Step number 13, construct the transfer function of the phase lag compensator. Since you already know what is a K alpha, 1 over T, and also 1 over alpha T from the previous step, you can produce a G lag of S. Then plot a new board diagram and check whether the design requirement is fulfilled or not. Okay. Alright, so for the example, we give you example 1. Design a phase lag compensator such that the system in figure 1 will have a 22% overshoot and Kp equals to 100. Okay, so this is the design requirement, 22% overshoot and Kp equals to 100. So this is the system G of S. So you need to put later on the controller G lag of S in front of the system. Okay, so for the solution, no requirement on the bandwidth, so proceed to step number 2. So from Kp equals to 100, we get the value of K equals to 2400. Then we plot the block diagram of G of S using K equals to 2400. So in order to plot, you can use Scilab, MATLAB, or you can use online software. Next, calculate the compensated phase margin. Okay, so we give you the overshoot of 22%, then you can calculate the damping ratio, which is 0.4342. From the damping ratio, then you can calculate the phi m. Okay, 46.23 degree. Step number 5, calculate the additional phase, which is phi m lag, which now you get the value 56.23 degree. Next, step number 6. From this step number 6, we will start to use the board diagram that you have plotted in the previous step. Okay, find the cross frequency Fg from the board plot that produce phi m lag equals to 56.23 degree. Okay, so yeah, already shown in this figure. Okay, from the phi m lag 56.23 degree, okay, you project a line, then you can find Fg. Okay, so now Fg is equals to 11. Okay, 11 radian per second. Alright, step number 7, find the magnitude value G or Gm at Fg from the board plot. Okay, at Fg, so Fg is 11. Project a line above until cross the magnitude line, and then project a line to the left on the y-axis to get Gm equals to 22 dB. Okay. Step number 8, draw the asymptote line on the magnitude plot at the magnitude of minus Gm, so minus 22 dB here. Okay, that will be the asymptote line. Step number 9, choose the location of value 1 over T, which is 1 decade lower than Fg. Okay, so Fg is 11, 1 decade lower is 1.1. Okay. Step number 10, draw a line from Fg over 10 until intersect with asymptote line and name it as point Q. Okay, so this is represented by the dotted or the dashed yellow line. Okay, from the 1.1 project until intersect with the asymptote line. Okay, and name it as a point Q. Alright, next, draw a line with the slope of minus 20 dB per decade from Q until 0 dB line and name it as point P. Okay, so this is given by this cyan color line. So I draw the slope of minus 20 dB per decade until cross the 0 dB line. Okay, So the cross section to 0 dB line, we call it point P. From point P, you project a line to x-axis, okay, and you got the value 1 over alpha t, which is equals to 0.2, okay, meaning that 1 over alpha t is 0.2. Then you can find what is alpha, okay. Next, step number 12, find the k alpha. Okay, this one you can use the formula in the step number 12. So k alpha is 10 to the power of minus 22. Minus 22 is gm, okay, the value of gm, over 20. So 20 here is a 20 log. Now the value is 0.0794. Then finally you can find what is a complete equation of a G lag. Okay. Next, plot the new Bode diagram, G lag of S and G of S, okay, together, and check the design requirement again. And note that the phase margin is 46.3, which is close to the desired design specification 46.23. That is correspond to the 22% of overshoot, okay, the design requirement. Okay, I think that's all for the phase lag compensator. Thank you very much.